Okay guys, welcome back to part 2 of Objective 3. I promise I will keep this video much shorter than part 1 as best as I possibly can, so let's just go to it. So, very first thing to talk about is liquids. So we talked about intermolecular forces, now we'll relate it to the behavior of liquids. So, as intermolecular forces increase or decrease, it will change the property of liquids. So liquids that have a higher IMF or stronger IMF will have noticeably different properties than one that has a weaker IMF, particularly surface tension, capillary action, and viscosity. So surface tension. If you can increase the attractive force between the molecules of any liquid, then that's going to increase the surface tension. So as this attractive force increases between all these molecules, the cohesion of the liquid increases and the tension across the surface of that liquid increases. Capillary action will also change. So capillary action is anytime you soak liquid into a small narrow tubing of some kind, so sponges are capillary action, filter paper, coffee filters. When we did chromatography, that was capillary action. So a liquid rising through very narrow tubing of some kind. So capillary action will increase with stronger IMFs. Adhesion will increase, so that is the force of attraction between a liquid and the container it's in. So you can see the meniscus here. This is mercury, so since there's not a whole lot of adhesion, the mercury actually gets pushed up in the middle and you get a bow out, whereas the meniscus for water, there's adhesion with the surface, with the walls of the container, so you get a bowing downwards for the meniscus here, so difference in adhesion. Same reason why drops of water will cling to glass more than drops of alcohol or oil, or mercury clearly doesn't stick to glass containers at all. And then, of course, cohesion will increase between liquids with stronger IMFs. And since that is increasing, that means viscosity will also. So higher viscosity, a higher resistance to flowing is indication of higher IMFs. Things like honey and molasses have really high viscosities, whereas like water, alcohol, oil have lower viscosities. So molasses and honey flow really slowly, whereas water and oil and all those things flow much faster. You can see glycerol right here. You have these 3 OHs, so these 3 hydrogens that are capable of hydrogen bonding with another molecule. So because it's relatively small and you have these 3 hydrogens that are capable of a strong IMF, it makes very viscous. This is the stuff that you use to make bubble solution. Solids. Okay, the other half of this whole thing. So looking at the relationship between IMF and solids, starting off with crystalline solids and amorphous solids. Crystalline solids are very, very organized. Ionic compounds do this because their charges are so strong. So they're extremely organized and well regulated. The example here is quartz, which is actually covalent, and then glass. These are both silicon oxide compounds, but this is very regulated, whereas this is kind of the cooling of the glass wasn't as uniform as this, so it's a bit more sporadic. You can see a little bit of crystallization that happens. So essentially the difference between, this is essentially the difference between, again, an organized crystal versus kind of chaotic structure. Types of crystalline solids: ionic, network, molecular, and metallic, so we'll kind of cover all of these. Ionic solids are using ionic compounds, so you have a positive and negative ion. They are extremely organized and very strong force of attraction between everything because it is ion-to-ion forces. Again, we're going to be careful of the phrase intermolecular because these things aren't actually molecules, they're compounds. And properties of ionic solids: high melting point, they're very brittle, low vapor pressure, poor conductors, etc. Network solids usually involve covalent compounds, so they're not as organized as ionics, and they're not as strong as ionics, or that force of attraction isn't as strong. Usually involving carbon or silicon. They can be 2D or 3D structures depending on how things are arranged. So the example here is silicon oxide, which is quartz. All rocks are some silicon oxide compound unless they're carbon oxide compounds. And those are all network solids. So gemstones of all kinds are some sort of network solid. Graphite and diamonds are network solids. So diamond is three-dimensionally held together, which is why it's so strong and it keeps its structure so well. Whereas graphite, which has the exact same makeup, they're both carbon compounds, has a different shape to that structure. It's more two-dimensional in its network, and then there's a slight attraction between the layers of graphite. So that's why when you write with it, you can scrape off the layers and you leave pencil marks everywhere. So really, graphite and diamonds, same idea, just different way the network is set up. So you can essentially think of these as failed diamonds. And then molecular solids, these are usually other nonmetals, diatomic or compounds. The strength of it depends on the IMFs, but generally they're low melting point, they're pretty weak. Ice counts as a molecular solid, so comparatively it's a weak solid compared to all the other options. And so yes, they're not as rigid, or they don't hold up to other forces as well. And then last, metallic bonding. So these are metals. They are going to involve just primarily a metal element of some kind with maybe something else built in, and they are usually very conductive, at least compared to the others, usually fairly malleable and very ductile, so you can pound and bend and shape them a little bit, and kind of go from there. They have a sea of electrons that we talked about before, so kind of the electrons are kind of free floating between the makeup, and you can use them to make alloys. So if you take a primary metal and replace parts of it with either another metal or another element, you can modify the properties to better fit what you want. So you can either make it more malleable or more ductile or better conductor or worse conductor, etc. So there's different examples of alloys right here, so brass and steel. Really the difference here is substitution versus interstitial. So substitutional, you are adding a new atom that is about the same size as the original primary metal. And then interstitial, you have smaller elements that are replacing parts of it. So pure metal, if you substitute something that is about the same size, you get substitutional. If you add in something that is noticeably smaller, it's interstitial, and then you can do both at the same time. Going back, brass is copper and zinc, which are right next to each other on the periodic table, so about the same size. And then steel involves iron and carbon, which have a noticeably different noticeably different size to them. So this is just kind of the general overview of all the different types of solids, and the forces that kind of apply to them, some of the differences in properties, and then some examples. So hope that clarifies, and let us know if you have any questions.